Okay, so next we have Kevin Dietz. I hope I pronounced that correctly. He's a staff data scientist at GitLab. Kevin will be presenting data science in the fast lane, accelerating model deployment with continuous integration and MLOps. In this session, Kevin will discuss how continuous integration and MLOps streamline data science workflows by automating tasks like data pre-processing, feature engineering, model validation, and deployment. Please give a warm welcome to Kevin.
Hi, good morning. To kick things off, I want to pose a question to everyone in the room. So by a show of hands, how many folks have trained a machine learning model in the last 6 months? All right, that's a good chunk. And how many folks have been able to get that model into production? Okay, a lot less. That's not uncommon. Oops, can we? That's not uncommon. I think we all know that model deployment is costly. There's a study from, or a survey from a couple years ago that showed that it takes 30 days or longer to deploy just one machine learning model if it gets deployed at all. And that 25%, oh, there we go, 25% of data scientists' time is spent on model deployment. So hopefully in the next 20 minutes, you'll learn some good insights on how we can speed up both the development and the deployment process of our models. To give a little background, my name is Kevin. I'm a data scientist at GitLab. For those who are not familiar with what GitLab is, it is a DevOps platform. It is built foundationally on the open source Git framework. I like to think of it as software for software developers. And what GitLab does really well is to make it more efficient for software developers to build, test, and deploy code. I think there's a lot of learnings that us as data scientists can gain from how software developers do their work. So I want to propose incorporating DevOps into our model ops or our data science strategy. So I think most folks in the room are probably familiar with data ops and MLOps. Data ops being those pre-processing techniques that we use to transform and massage the data into how we need it for our models. So things like dbt, even Airflow to orchestrate those workloads. And then model ops are the ways that we manage and govern our models. Things like model registries or MLflow. And I think I want you to start thinking of how you can perhaps use DevOps to complement these other two. And within DevOps, there's two principles that I think we can really leverage within the data science world, and that's continuous integration and continuous delivery, sometimes referred to as, often referred to as CI/CD. What are these? What do they mean? Continuous integration is simply just a way to continuously build, test, and deploy our code. So we can continually test, build, and deploy our models. And at the other end of that is continuous delivery, a way that we can seamlessly put into production our code or our models more effectively and with less time. There are, I think, 4 main advantages to using CI/CD for data science in terms of automation, scalability, iteration, and reproducibility. So let me go into those all briefly. From the automation perspective, we can use CI/CD for our data science processes to develop our models faster in less time. We can set up these automations that will reduce the human error element to what we're doing. And it makes it that much easier to update production models that we do have. From the scalable side, we can put the right model resources for each model. So we can scale up or scale down the resources as needed. So it's a really cost-effective measure. We don't have something that's always on. The model is only running and consuming the resources that it needs. From an iterative side, we can do really rapid experimentation with CI/CD. We can test multiple models at once. We can collaborate with our coworkers on models to make it a really iterative and collaborative process. And finally, I think this is perhaps maybe the most important one, just from a headache perspective, is we can reuse a lot of the same elements, a lot of the same pipelines across our models. And so it really reduces the overhead and the setup to get our models up and running. And it makes it a lot easier to maintain and to monitor. Oh, and there we go. And it results in faster, more efficient model development. OK, so I'm going to dive into an actual demo in a couple minutes. But before I do that, I want to dive into kind of specifically how we're going to use those 4 principles in that demo. So from an automation perspective, we are going to use CI to build automatically our training and our production environment. And those pipelines are also going to automatically log everything about our model. So the logs of the model themselves, but also the model runs to an experiment tracker. It will also upload every artifact from every run to an artifact repository. So we have a record of what happened and when. From the scalability perspective, we can increase or decrease the CPUs or the RAM that we need. We can switch over to GPUs if we need them. And it allows for really fast concurrent training. If we're training things on your local laptop, right, you're kind of restrained by the resources that are on your laptop. But if you're running things in CI, you could run 10 iterations of a model at once if you really wanted to. And from the iterative side, it makes it really easy to track model results and the performance of our models. And we can set up model review processes with our coworkers and approval flows, just how they do it in the software world using DevOps. And finally, from a reproducibility standpoint, everything that we're running in CI is containerized. And so that makes it really easy for someone else to pick up your work and run with it. So if I'm here giving this talk, one of my coworkers could pick up a model that I've been working on and run it with no issues. Because it doesn't matter if I have a Mac and she has a PC. It's really platform agnostic, because we're running everything within these CI pipelines. So I'm going to jump into an example. I put a big old QR code up there. I'll put it up again at the end of the talk. But this links to one of our handbook pages that has very detailed instructions on how to reproduce everything that I'm going to walk through, as well as links to things like the repository that I'm going to be using. So I'll put up again at the end as well. So I'm going to jump over to, So I'm going to jump over to this repository. So this repository, if you use GitLab, it probably looks pretty familiar, pretty standard stuff. We have things like a Docker file, a requirements file. That's what builds our container. It tells us what Python packages we might be installing to run our model. We have this CI YAML file. This is the brains that tells us how we want our pipelines to work. I'm not going to go into a lot of detail about it, but this is also available in that QR code. But basically, it lays out for every job that's part of our pipeline, what is that job doing, what container is it using, what process is it using, how does it work? So that's also in there. We have some configuration files, probably pretty common to when we develop models. This one's really simple. It's really just a couple model parameters. And then what do we want to name our run or our experiment in MLflow to track it. And then we have our notebooks. One thing that we do for our own internal data science models is we run everything, training models, production models, we run everything using notebooks. We find that actually works really easy. We don't have to convert things over, and it just works. So I have a training notebook in here. Pretty standard. We're just importing our packages. This example, it's using one of the toy data sets from scikit-learn, I think the breast cancer data set. But you know, you can connect it to your Snowflake environment, to your SQL tables, all the same to pull in data that way. But this example, we're just going to use a sample little toy data set. It's going to run a XGBoost model, and then we're just we're just going to spit some things out at the end to MLflow using that MLflow API. So I'm going to jump over to the GitLab web IDE. You don't have to use this. You can use any IDE. You can use JupyterLab. You can use VS Code. You can run it in the command line if you are so inclined. So all I'm going to do here to initiate our training run of this model, I'm just going to rename the model. I already have one run called Model 2, so I'll call this Model 3. And then to activate our pipeline, what it does is it activates by the commit message that is pushed to our merge request, often called a pull request in other platforms. So to activate our training pipeline, it's just train, and then the name of our notebook. I believe our notebook is in Notebooks. And it's called training. Oops, did I miss it? It is called training example. So if I send that commit to our merge request, it will initiate a pipeline to start training that model. So if I pop over to the merge request I already created, you can kind of see it just initiated it. So if we pop over to our pipelines, we see that it is now running our training run of the model. I'll pop into that. There are 4 jobs that it is going to do as part of this training process. Oh, I should also mention, everything I'm showing, you can do for free in GitLab. You don't have to pay for any of this. So it's going to build our container, which is what this job does. Then it's going to run that training notebook in this job. It's just going to run it all the way through. And then it's going to push some model metrics out to the comments of this merge request so we can see it. It's also going to push things out to an experiment tracker and log those artifacts. And then finally, I just threw this in here because I think it's kind of cool. It does a little secret detection just to make sure we're not exposing any passwords or credentials accidentally in our pipelines that will show up in our logs. So it's going to check for that as well. This usually takes a minute or 2 to run. I've already run one. So if we go back to this, we can kind of see in the comments, it logged kind of some basic model metrics right within the comments. So I could tag a coworker to say, hey, can you review this? Does this look good? We can kind of see everything about it. We've also, it also shoots out to an experiment tracker. So we have one built into GitLab, which I'm showing right here. So we have our different runs of our models. If I want to click into one, it's going to show everything you would expect in a model tracker or MLflow. We kind of have our model metrics, some model performance things. We can see the CI job that it ran from, as well as a link to all the artifacts associated with it. So if I click on artifacts, it's going to kind of show the artifacts that I chose to log for this model. And say we like this model, we want to put this model into production. To do so, it's pretty easy. Instead of using that train pipeline, we're going to use a score pipeline to make sure that the model will score appropriately. So if I go back to our IDE, I will invoke our scoring pipeline using the score command, and I think it's called scoring example. And this will launch our scoring pipeline. The reason we have 2 separate pipelines, one for training, one for scoring, a couple of reasons. One is they require different resources. Usually when we're training, we want more power. We want more CPUs. Maybe we want to use a GPU. When we're scoring a model or serving a model, we don't need that many resources. We can make it more bare bones. And also, we want the pipelines to be slightly different. When we're training models, we're logging a bunch of stuff, maybe to an experiment tracker. When we're scoring a model, maybe we want to be notified if that pipeline fails. But we don't necessarily care if it fails in training because we're actively monitoring it. So there's a few differences for why we have 2 different pipelines. But we can see here that scoring pipeline, it's running now. Once it's done, I could tag one of my coworkers to review the model. She might look it over, said this looks good. And then we can merge it into our main branch of our model repository. And then from there, there's not much more we have to do to get it into production. What we use internally is we use tags to tag releases of models, similar to how software developers create new versions of code. And so we do that using the tag feature in the repository. And maybe we create a new one called 1.1.0. Oops. And we're going to create a new release of that model. And then from there, it depends how you serve your models. Maybe this goes to Airflow to do some type of orchestration. A lot of our models internally, they run in batch. They run every day, every week, whatever. And so to run them in production, we use CI pipeline schedules. That's all we do to make our models run automatically in production. And to do so, I just have to update the pipeline to use the old version of the model to the new version of the model. And I save that, and next time this model runs, it's going to deploy that model using the new version. So let me pop back. So that was a really quick demo. I know I threw a lot at you. I'm going to throw a little more at you. There's a lot that you can do with CI pipelines. Beyond that, I kind of touched on the security scanning aspect. You can introduce a whole host of security scanning to your models to make sure that you're not using packages that might be compromised, that you're not exposing secrets or passwords into any of your pipelines. You can use things like a CI catalog. This is what we use internally. So we have kind of one place where all of our CI sits, all of our CI code sits, and we can use that across all of our models. So we don't have to update kind of configuration files in multiple different repositories. We can update it in one place, and it will propagate to all our models. You can also tie this into model governance things. So like a model registry to look at versioning and lineage. You can even have it auto-deploy new releases. There's a lot you can do. We tied it just to the experiment tracker, but you can imagine this ties in nicely to a model registry as well. And finally, you can also set it up to do some monitoring, to look at drift detection. And maybe if it monitors the performance of the model, and if it notices the model performance goes below a certain threshold, it will trigger a CI pipeline to do an automatic retraining of that model to improve the accuracy of it. So a lot you can do, barely just scratching the surface. I know I threw a ton of information at you. So I'm going to put that QR code up again. That links to everything I discussed, as well as that repository. Please fork that repository, play around with it, see how it can meet your needs. And it's a great resource to use. And with that, I thank you for your time. Questions?
Thank you for. Hello. It works. Thank you for your interesting talk. I have a question about monitoring and drift detection. If I didn't serve the model using GitLab, I serve the model to any endpoint, like a cloud function in Google or something like this. Could I be able to monitor also my model using GitLab monitoring?
I don't know about GitLab monitoring. That's not my area of expertise. But if you're passing model metrics back into CI or as an output of CI, then you absolutely can monitor that and log those log that performance and monitor to see when it needs to be retrained.
But data drift is not about the performance only. We have to check the drift like on the data itself, right? So you need also to buzz the data.
Yeah, so
not only the scores.
Exactly. Yes. Yeah, so as the data is coming into the model, you can have some processes to look at that, and it can perhaps in that pipeline it's going to flag if the data has changed significantly. So you can absolutely add that to your model components.
Thanks a lot.
Hi. Thanks for the presentation. I have a question. If you have any branching strategy that you guys use when you work, say for collaboration, but also for model deployment?
Yeah, our branching strategy is basically feature branches. So we have our main branch, and then if we're working on a feature, in our case, maybe a new iteration of the model, that's a separate branch. We toyed around with having like a development branch, a production branch. We found it too cumbersome. We found that tags actually work really good. So we have our main branch, and that is our, our source of truth, and then it's just feature branches that feed into that, and then we deploy based on tags.
A clarification. Yeah, you mentioned that you have an integration with a MLflow. I assume that also the model use the model registry of MLflow, right? So the model itself is not persisted in GitLab.
Yeah. So we have a model experiment feature in GitLab that is based on the open source MLflow APIs. So the APIs for MLflow work for ours. I know we are in the process of building out a model registry as well. I don't know what APIs those are going to use, but I imagine it'd be similar.
Thanks.
Hi, thank you for the talk. So I have two questions. First is, can you specify external runners so that you can run larger, let's say, workflows rather than use the ones that are provided by GitLab? And the second question is, how much of this is available in the community edition of GitLab? Because you can also self-host GitLab as far as I know.
Yeah, there's a ton of different runners that you can use to scale up, scale down. I think you can bring your own runner as well to run these pipelines. And yeah, this is all available. You can run all this in the free or the community version of GitLab. You're only kind of limited by the size of the runner that you're able to use for some of this stuff. So if you need a bigger runner because you're running a large model, that might not perhaps be available.
Okay, thank you.
Great, thank you.